Okay, welcome everyone to the Astronomical Society of Edinburgh, wherever you are. We've got people here in the church in Edinburgh, the Augusta United Church. We have other members on our Zoom feed, and we have visitors on our YouTube channel as well, so welcome wherever you happen to be. So this is what we've got coming up tonight. Just a few slides from me, what's coming up over the next few months. And then our main speaker for the evening is Dr. Thomas Wilson from the University of St Andrews, telling us about the life of a planetary system. Our president, Sean Wickstead, will tell us about the sky in March. And at that point, we're going to turn off YouTube for visitors and say goodbye to you. Thank you very much. For members only and anyone else in the hall here, I'm going to give a rundown of our plans for a new remote observatory that we're currently working on as well. Yep. If you haven't been with us before, there's lots of ways of staying in touch with the society, and we have a website where everything we're doing is on there. All the upcoming speakers, any events that we're running, lots of information on Facebook and Twitter, and a lot of the videos from the past few years are on our YouTube channel as well, so there's some amazing stuff in there if you want to dig around through that. And on our Flickr group are images that some of our members have created, and they are getting better and better all the time. Some amazing images on there worth having a look at. So this is what we've got coming up over the next few months. On the 8th of March, on Wednesday next, we have our Imaging and Observing Group, and that's for members only. And we're fortunate to have Nick James of the BAA coming to tell us about observing comets. He knows absolutely everything there is about observing comets, so that should be really good. 17th of March, an online-only talk from Dr. Roberta Zanin on the Cherenkov telescope array. Next month at this time, on the first Friday of the month, the 7th of April, we're having a members' night. So that won't be on YouTube, but it will be on Zoom for members. It will be here, and any visitors are welcome to pop into the church as well. And that will be a number of short presentations by members. And Alan Pickup will give us his comprehensive sky in April. That's always worth listening to. Our monthly Imaging and Observing Group again. The 21st of April, an online-only talk from Dr. Michaela Musilova. About simulating missions to the Moon and Mars. 5th of May, again in person here and on Zoom and YouTube. Introduction to Cosmology in the 21st Century with James Webb and Gary Filders. 19th of May, online only, will be Indigenous Australian Astronomy from Dr. Pete Kuzma. And on the 2nd of June, one of our honorary presidents, Professor Andy Lawrence, will tell us about 200 years of astronomical images with the Royal Observatory. So lots of good stuff coming up. Feel free to join us when you can. But that's it from me. So over to our speaker tonight, Dr. Thomas Wilson. I'll get out of the way. Give you that as well.
Thank you. All right. Hello, can everyone hear me? I can hear myself, so I'm assuming that's a good sign. Fantastic. All right. Yes, so thank you, Mark, for the introduction. My name is Dr. Thomas Wilson. I'm a research fellow at the University of St Andrews, specifically working in the Center for Exoplanet Studies, where I use some of the telescopes I'm going to talk to you about tonight to characterize exoplanets across our galaxy to see what we can learn about these planetary bodies. This may work. Okay, let's do it the old-fashioned way. There you go. So in today's talk, I'm going to give you kind of an overview of the life of a planetary system, right? We may know a lot, or you may know a lot even, of the current state of a lot of planets, right? We all live on a planet, so we kind of know what's going on the day-to-day, mostly. But I want to break it down and tell you how planets form in the beginning of the talk, and answer the question, how do planets form? Then I'll move on to the second part of the talk where we'll take planets that I've just described how they form. They are now adult planets that have gone out and have to get jobs. and we are now looking at how they evolve over time until they die. So we're going to have 3 sections of this talk: how they form, how they evolve, and answering such questions, or trying to answer such questions, are there Earth-like planets out there? And then finally, something you may not have thought about before unless you've read or watched science fiction, what happens to planetary systems when their stars die? And in this part, I'm not going to be talking about aliens or Death Stars or anything like that. It's more going to be about when stars go supernova or go into the white dwarf phase, what happens to the planetary systems around us, such as the Earth will, or what the Earth will go through in about 5 gig years' time. The life cycle of a star, now you might not think this is very related, but obviously planets don't isolate, right? There's no self-isolation in planetary systems, and they evolve around stars themselves. So we kind of have to start by looking at the life of a star. And fortunately, for over 100 years of work, we know the life cycle of a star pretty well. We start over here on the, hopefully you can see the cursor online as well. We start over here with a giant molecular cloud full of gas and dust that, depending on the mass of that cloud, will evolve into either a small star like our sun that will eventually go into a red giant and ultimately end up at a white dwarf star, such as our sun will go in about 5 gig years' time. Or if they're slightly more massive molecular clouds, it will evolve into a larger type star, a red giant, and eventually go supernova into either a neutron star or a pulsar if it spins, and then a black hole at the end of this. Now, as I mentioned, thanks to about a century's worth of work, we know the life cycle of a star very well. But for planets, that's not really the case. We don't have this kind of unifying timeline that I can just point to and say, okay, this is what a planet will go through. So we kind of have to piece things together, starting with the formation, or at least this is how I describe it in my talks, starting with formation, moving on to evolution, so kind of planetary systems in the main lifetime, and then ending with the destruction of planets. But these are all separate fields, and so there are a lot of question marks on how we go from one stage to the next, and then to the end stage. And of course, with research, as with everything, there are many questions within those fields themselves. So hopefully, by the end of this talk, all of these question marks, or at least most of these questions, will be resolved. What I like to do in my talks is not just tell you what things are like. I don't want to just say, this is what's happening and you take my word for it. But I like to show a few so-called case studies in which I will highlight a telescope that we use for various science, put it up on the screen, and then on the next slide, I'll show you what data we might get from that specific telescope. So here is an example, just to kind of show you the overall kind of thing of what I want to do here. This is the Isaac Newton telescope. It used to be in Herstmonceux down in Surrey in England, but in the 80s we realized that British weather sucks, and so we moved it down to La Palma in the Canary Islands in Spain. And this is what it currently looks like. It's a photo taken by myself a few years back. With the Isaac Newton telescope, there's a whole range of science you could do, but something that I've been particularly interested in is the discovery of near-Earth asteroids. And myself and some collaborators 5 years ago now, in 2018, discovered 2 new near-Earth asteroids using the Isaac Newton telescope. So you can see the animated GIFs over here on the left. We have 2018 VQ1, and on the right, 2018 VN3. Hopefully you can see with the kind of red circles there. So this is an example of what you could use the Isaac Newton telescope to do. So, starting off, formation. How do planetary systems form? Well, as I mentioned before, if we want to understand planetary systems, we need to understand stars, and so I'm going to touch very briefly on stellar evolution. This is an overall schematic of how a star and a planetary system will form. We start off with a giant cloud of gas and dust somewhere in space. It's not doing much, it's kind of just there by itself. And then at some point, it will get a kick. In the solar system, we think this was from a nearby asteroid, but this could nearby supernova, sorry, but this could be a passing star or whatever. And then, due to this kick, it will start to spin on some axes, gravitationally start to collapse in of itself to form at the center. and you can see down here at the bottom, I know I've skipped a few steps, but you'll have to trust me that we get down to this stage down here and form a protostar in the center of this, this gas and dust cloud. Now, because it is spinning, that means that due to the conservation of angular momentum, right, the gas cloud will form into this kind of disk here. And so that any material that doesn't fall onto the star itself will still remain in this disk. And this is what forms planets. So this is what I'm going to focus on for the remainder of the talk. I'm not going to mention anything in the previous steps, but if you're interested, we can talk about it after. So there are 3 stages to forming a planet. If you start over on the left side of this, this slide here, you can see that we have star formation and kind of this gas cloud that I mentioned before. And then observationally speaking, we have 3 steps. We start with a primordial disk, then move on to what's called a transitional disk, nicely named because then it goes into a debris disk. This happens over about a gigayear's timescale. You can see in the middle here some timestamps of what we think this is happening. And then at the end of this process is when you'll go into a planetary system. You'll kind of have just a normal, boring planetary system at the end here. The theory says that at these different times, we should have different things going on, right? In the primordial disks, to start with, this is when gas giants will likely form, such as Jupiter. And then moving on, after about 5 million years, we should have terrestrial planets, such as Earth. And then lastly, we'll have these what's called disk clearing events, in which comets and asteroids will start sweeping up a lot of the material left in the debris disk. One such example, and one famous example of a primordial disk, is V883 Orionis, which I'm showing here on the screen. As you can see, there's not much going on here. This is the very start of a planetary system's formation, right? It looks, we have a bright feature in the center here, which is the protostar. Not much is going on. And then if we move away from the center into the outskirts of this disk here, we can see it starts to get a little bit fainter, and then fainter still, and then even fainter still, until we get out into the edge of this system. I've noted on here the current orbits of Neptune and Pluto, so you can get an idea of the scale of this disk, but you can see it's quite massive in and of itself. So, the first case study, this is what I want to hit you with straight away. This is the Atacama Large Millimeter Submillimeter Array, also known as ALMA. Some of you may have heard of this. This is a series of between 30 and 50 radio dishes down on a plateau in Chile. You can see one such configuration here. ALMA has been used to study a whole bunch of science that I'm not going to go into in detail, but what is pertinent for this talk is that it can image dust very well. And that is what we're thinking about when we want to study planet formation. So, this is one image from ALMA, right? Now, the eagle-eyed amongst you might notice that it looks very similar to the image 2 slides ago, and that's because I cheated a little bit and put the data from ALMA in my second-to-last slide. This is why the images look very similar. But this one, instead of Orionis, this is of HL Tau. And you might notice that this is markedly different from the image I showed 2 slides ago, in the sense that, okay, we do have a bright central region here, but we seem to have all of these rings, right? We seem to have these dark features going around in either circle or elliptical orbits around this host protostar. And this is because what is currently going on in this system is planet formation. We have gas giants such as Jupiter and Saturn being formed in this system right now. And we can only observe this with instruments such as ALMA. This is what the theory really tells us is happening, so hopefully this is working online as well. So over on the right-hand side of this slide, you can see some simulations of what we think is going on with the dust in this planetary system. So we have small particles that kind of agglomerate together in some fashion, and then when they get large enough to maybe pebble-sized, the gravity of those pebbles will start to attract more dust, and then they start accreting more dust and more dust and more dust, all the way up until you get to a planet-sized. We'll see that more in the next slide. And then when these planets get more massive, they can start accreting gas, which is on the left-hand side of this animation here. and they can start to carve away more of the gas in a protoplanetary disk, as we should. Well, we didn't really see it, but we'll see it in a bit. And then this is how you get into gas giants, to forming gas giants. This is a little bit more detailed video of how it works. So if we zoom into a protoplanetary disk here, then if we zoom in, there you go. Okay, we can start to see some dust particles that are moving across the screen here. Now, if you've ever smoked or been around a smoker, you can think of these dust particles are roughly the same size as the vapor or the smoke that comes out the end of a cigarette. So if you think about cigarettes and the smoke that comes out, that is basically what we're looking at here, this kind of size of particle. Now, as you can see, they start coming together to form these pebbles, and those pebbles themselves start to gravitationally interact and bring a lot more of the dust together until we're forming boulders and then asteroids, and then the asteroids hit each other and gravitationally interact to form protoplanets or planetesimals, and then lastly, we ended up with planets, so Earth-like planets or Jupiter-like planets in general. Fantastic. So that's what goes on in the first two stages of planet formation, right? We have the primordial disk, and then we have the transitional disk. But one of the most exciting phases, I think, is the last stage, which is so-called debris disk stage, in which, as you can see from this Hubble image of the Fomalhaut system, it doesn't really look a lot like the ALMA observations. Now, partially this is due to it being a different telescope, of course, but also because there is not much gas and dust left in this system anymore. We have blocked out the light from the host star in the center here, so this is kind of what the black hole in the middle is. That's not an actual black hole, that's just us blocking out the light from the host star. Using a coronagraph, you can still see some of the light around it. But what's relatively interesting about this system is that using Hubble, over a series of observations from 2004 to 2012, they found a small bunch of pixels that are moving in a very predictable manner. And they are moving on an orbital motion because this is one of the youngest exoplanets that we've ever discovered orbiting the Fomalhaut star. This planet will be on the order of tens of millions of years old, so it'll be very hot. It will still have a lot of latent heat from its formation. So there's probably no life on it, to be honest. But it's an interesting system nonetheless. You can also see in this image a gas ring here. So if you think something like Saturn's rings, just scaled up quite a lot. I've mentioned a lot that protoplanetary disks have a lot of dust, and that's because in the inner parts of these systems, it's very hot. The temperatures are on the orders of thousands of Kelvin or thousands of Celsius, something like that. And so gas cannot really survive, or ices cannot really survive interior to what's called the waterline, right? And that's this feature here. So interior to this, you might have rocky planets such as Earth or Mars or Venus. And then outside of this, we have more gas giants such as Jupiter and Saturn and stuff like that. This is quite important, the fact that there is ice there as well as dust, because we can use this ice to make a link between the present day of planetary systems and their formation in and of itself. And I'll talk about this over the next few slides. So over on the left here, we have the HL Tau transitional system, which I've talked to you about before, and this is all kind of dust that we see here from this ALMA observation. But because on the outskirts of this system we have ice, if the ice does not move closer into their host star, then it will stay relatively primordial, right? Nothing's changing if we have ice further out away. And what forms further out in planetary systems? Well, it's usually comets, right? We think comets form at the outer edges of these planetary systems, and so if those comets do not go closer into their host star, any ices or gases that we observe in comets should be relatively indicative of the protoplanetary system, so protoplanetary disk. So we can make a link between current observations of comets and how, for example, our solar system formed. One such example of this is the Rosetta mission, which you may remember of from about a decade ago, This was ESA, or European Space Agency's spacecraft that went and visited the comet 67P Churyumov-Gerasimenko and did a whole bunch of fantastic science. But what I want to kind of share with you today is this list of molecules that was found by Rosetta on the comet 67P. Now, you can see this cometary zoo, as it's been named, contains quite a lot of molecules. For example, it contains some alcohols, such as methanol and ethanol. It contains some smelly and colorful molecules, such as sulfur. But intriguingly, I think, is the so-called king of the zoo, as it's been named in this press release, is the molecule glycine. Now, if anyone did biology in school or has avid interest in biology, glycine might just start ringing some bells here, because it is a precursor to amino acids, which themselves are precursors to DNA. And so what we have found on this comet is a precursor to DNA, which is, of course, a building block for life. So I'll let you make your own judgments on if this means there are aliens in our outer solar system or not, but it's still quite an interesting result nonetheless. The second part of my talk, I want to discuss the evolution. So we formed a planet either through the primordial phase for gas giants or the transitional phase for Earth-like exoplanets. But now what happens in their main lifetimes, right? How do they evolve, and are there Earth-like exoplanets out there across the galaxy, or are we really alone? Solar system missions such as Rosetta and some of the others that I've touched upon already are great, right? They are fantastic. We can go and look at our 8 planets and moon and asteroids, comets, dwarf planets, all that. They can tell us a lot. I'm showing here a diagram of a lot of the ESA, so the European Space Agency's missions, but of course there are NASA, the Canadian Space Agency, the Japanese Space Agency that are sending missions all the time. And this is fantastic for learning a lot about our solar system, but it really is only one planetary system. And why I highlight this is that the very first planetary system that we discovered back in 1992 was 3 planets orbiting around a pulsar. Now, if you remember from my second or third slide, a pulsar is just a spinning neutron star, which is a star that's gone through supernovae, right? So how on earth are exoplanets surviving around a dead star that's just gone supernova? This is obviously, back in 92, this was a fantastic discovery, and this is quite different from the solar system, you might agree. So maybe we need to look further. Maybe we need to study more planetary systems across the Milky Way, and we have 3 main methods to do that, which is what I'll talk about over the next few slides. And then I'll briefly touch on how we can kind of study exoplanet atmospheres, and this is quite pertinent now with the launch of JWST. And lastly, I'll highlight a discovery, in quotation marks, of an exomoon, which is still very tentative, and I don't think many people in the community agree with it, but I just want to bring it to your attention anyway, as it is an exciting area of research. So you might already know this, but one of the main methods that we use to find exoplanets is the so-called transit method. So hopefully this works. Fantastic. So if we have a star out there in the galaxy, right, and we point our photometer at it, and we observe a dip in the amount of light that is coming from the system, we can this is one way in which we can detect orbiting exoplanets, right? If an exoplanet comes between us and its host star, similarly to the moon coming between the sun and us during an eclipse, then we can detect the amount of light that drops from the system and say, okay, there is an exoplanet around this host star. As you can imagine, if a planet is larger, for example, it's going to block out more of the light that's coming from a given star, and so it's easier to find larger planets, such as hot Jupiters. To give you an idea of the precision that we are getting to with modern-day instruments, just to kind of make this maybe a little bit more approachable, imagine, if you will, that I'm standing in a lighthouse on one of the towns on the south coast of Fife. Let's just say it's Anstruther, for example. And I'm in there in a lighthouse that I've just magically built, and I move a 10p piece in front of the lighthouse. And you're here in Edinburgh, and you can detect that 10p piece going in front of the lighthouse. This is kind of the level of precision we are getting to with these with modern day instruments, and this is why we can find such fantastically small exoplanets using the transit method. The next kind of most popular exoplanet discovery method is called the radial velocity method. I'll just describe this now. It's a little bit more in detailed than the transit method, so we can take it a little bit more easy here. If we were to point our telescope at a star, right, there are molecules in the stellar atmosphere here, such as hydrogen and iron and magnesium and calcium, for example. And the light internal to a star is going to get absorbed in the stellar atmosphere by these molecules at very specific wavelengths. These are called absorption features, and when this animation loops back around, you can see the spectra of these features shown as dark black bands here in this kind of rainbow spectra here. So we know that, for example, this band over, or these dark lines here might be due to hydrogen, and further along they might be due to iron and stuff like that. The important thing to take away from this is that we know very well at what wavelength those absorption features are. If a star is by itself, it's just kind of chilling out there in the galaxy, nothing is going to change. These absorption features are going to stay exactly where they are. But if a star is being orbited by a planet or by another star, for example, the gravitational interaction between the orbiting body and the host star is going to mean that the system itself and the star in the center here is going to orbit around a common center of mass. And you can see here that the star in the center is moving in a tiny little circle with the center just being outside of the circle, outside of the stellar surface. What that means is that the star at some point is moving away from us and it's moving towards us, which obviously the velocity of which, is meaning that the wavelengths of these absorption features are shifting to the blue as it's moving towards us and to the red as the star is moving away from us. And we can detect those shifts in wavelengths. So these black lines that are moving left and right here, we can detect them now very well. And I say very well because with current modern instruments, we can detect a star that is moving away from us or towards us on the scale of 1 meter per second, right? And that is walking speed, right? So that means that we can detect a star moving away from us at the speed that I'm walking across this stage, which is pretty crazy if you think of it. This means that we can detect down to Earth mass planets and sometimes even Mars mass planets, which is quite useful because this method is mainly used to find more massive planets, as you might imagine. These two methods are mainly used to infer the presence of planets, right? We're not actually observing them. We're just saying, okay, the amount of light has dropped, or okay, the spectrum is shifting from red to blue. So the third method is just direct imaging, right? It's just taking our cameras, pointing them at a planetary system, and seeing if we can detect the planets themselves. This is a famous example of this. This is HR 8799, in which a couple of colleagues of mine pointed, I think this is the Keck, this is a VLT telescope at this system and found 4 planets orbiting this host star, right? We have these 2 planets here you can see quite well. We have the planet on the outer edges of this system, and then even one that's quite close by to its host star that we're again blocking out with the coronagraph here, well detected. I say this planet in here is quite close into the host star, but if you look at the scale at the bottom of this video, you can see that that's about 20 AU or 10 AU maybe even away from the host star. So this is still much further out than Earth is in our solar system. So we can simply just take images of a planetary system to find fully fledged planets, but we can also link this back to our protoplanetary disk studies and find planets within the disk themselves. This is a famous example in which, if I just loop this, we can see here in yellow the planet even Beta Pictoris b, which is moving either behind or in front of its star. We can't really tell the distance here. But what is curious is that the kind of black smudge that you may be able to see in the back of the video is the protoplanetary disk that I talked about before. And so this is a planet that's still within its disk that we can directly image today. So my next case study is the Kepler mission. You may have heard of this space telescope before. This was launched, I think, in 2008, if I remember well. Here is an image of it in the clean room prior to launch, and you can see some of the engineers and technicians at the bottom here, just to kind of give you a scale of how large this space telescope was. Kepler did a fantastic job of detecting exoplanets. It used the transit method, which I've talked about before, in order to find almost, or over even, 2,600 exoplanets. And just to put this in some kind of perspective, before Kepler came along, we didn't really know of that many planets. We were detecting maybe a few tens a year. And then Kepler came along and found thousands of them. It looked at 500,000 stars, and it found over 2,000 planets over 10 years. And so this really kind of revolutionized the exoplanet field in that we now know that planets are everywhere, right? It's not just that there are a handful of planetary systems in the Milky Way, but they're kind of, all over the place. This is detailed more in this plot, which shows the discovery year of an exoplanet against the number of exoplanets that we found. And you can see for the 90s and early 2000s, we were kind of trundling along with a few tens of planets discovered, mainly via the radial velocity method here in red. And then when Kepler launched in 2008 and started to really kick into gear in 2010, you can see that the green slice of these bars just rapidly increases. So much so that in 2014 and 2016, the Kepler space mission discovered thousands of planets by itself. It really has been, I can't understate how much of a driving force it has been in simply discovering exoplanets out there. This has been followed up, of course, with the TESS mission, which you may be familiar with, that is currently observing the whole sky now. But of course, we can go ahead and discover exoplanets, right? We can go and use the methods that I've talked about to find these bodies and kind of put them in our catalogs and in our libraries and say, okay, there is a planetary system here. But actually, we want to go further than that, right? We want to actually know what's going on these planetary systems. And so this is where my next case study comes in. This is the CHEOPS Space Telescope. This is a relatively small space telescope. The mirror is about 30 centimeters across. The whole telescope itself is about the size of your washing machine, just to kind of give you some perspective. This is an artist's impression, of course, not an actual photo of the telescope. But the goal of the CHEOPS mission is slightly different from Kepler, in that Kepler was going and finding new planets. CHEOPS we have sent up to study the radii of planets in more detail so that we can characterize the planets themselves better. And what I mean by characterize is that if we measure the radii of these planets very precisely, we can potentially get a good idea of the interior structures of these bodies and learn, okay, are they somewhat like Earth? Are they somewhat like Venus? Or are they somewhat like Saturn or Jupiter for the larger bodies? One such example of this, and this is the data part of this case study, what I'm showing here is a transit of Kelt 11b. This was the first observation that we took using the CHEOPS spacecraft. And you can see kind of what I showed in an animation before, right? That we have the out-of-transit baseline up here where we're just observing the star, right? We haven't seen an exoplanet yet. And then at some time, so this is a flux against time plot, at some time the planet, in this case Kelt 11b, goes in front of the host star, Kelt 11, and blocks out some fraction of the light that from this star. And then a couple hours later, the planet leaves the stellar disk, and the amount of light that we're seeing from this planetary system returns back to just being the star, basically. What was quite interesting about this observation is that Kelt 11b is a hot Jupiter. It has a radius of about 1.3 times that of Jupiter, so this is quite a massive body. But with this CHEOPS observation, we were able to intrinsically know the size of the planet to an uncertainty of 1,700 kilometers. Now, that may not mean much, but that means that we can measure the size of this planet, this giant planet elsewhere in the galaxy, to a smaller distance than Edinburgh to Rome, which is quite mind-blowing if you think about it, really. A lot of people are interested in giant planets. For my research, I am more interested in small Earth-like planets. So I have been using the CHEOPS spacecraft to instead learn about the interiors of Earth-like planets for the first time in general. What I'm showing here is a result that we put out a few years back, and there was a press release by the University of St Andrews in 2021, which is the study of the system TOI 178. Now, it's not a great name, I'll give you that. We can talk about why it's named TOI 178 after if you're interested. But it has, so that we found, 6 planets, B, C, D, E, F, and G. Again, boringly named, but nicely catalogued. What we did is that we used the CHEOPS space telescope to measure the transits of these planets, as I showed on the previous slide, to accurately determine the size of these planets. Then we used ground-based telescopes with the radial velocity method to get the masses of these planets. So now we have the radii and the mass of each of these planets. We can combine them to learn about the density of these exoplanets. And then combining that with solar system models of, for example, Earth and Mars to know, what's going on in the interior structures of Earth or Mars or Venus, for example, we can then get an idea of what the interior structures of these planets further out into the galaxy are. For example, we have planets B and C over here on the left-hand side of this slide, which from our observations and from our analysis, we find that they have very large iron cores and silicate mantles, shown here in brown, with a little bit of a water layer on top, shown here in blue. So these might be ocean planets, for example. But you'll notice down at the bottom here, I've listed the temperatures of these planets. And you can see that the interior two bodies, planets B and C here, have equilibrium temperatures, so this is temperatures on their surface, of 1,000 Kelvin or 870 Kelvin. So these are very, very hot bodies which likely don't have an atmosphere. So it's likely that the atmospheres have been completely stripped away, and these are probably just ocean worlds. If we move further out into the planetary system, where we can see planets D, E, F, and G have similarly sized cores, they might also have very large oceans on top of that, again here in blue. But also on top of that, they likely have a large atmosphere here shown in gray. So we can see these might be somewhat more similar to Neptune than they are to, for example, Earth or Mars. Why are we doing this? Well, of course, the reason we are doing this is to find planets that are similar to Earth. And this is where an exciting metric comes in, called even the Earth Similarity Index, developed by PHL in the US. This takes a lot of system parameters, so this might be the planet mass, the planet radius, the temperature of the planet, the size of the host star, the orbital period of the planet, and stuff like this, and the irradiation of the planet, for example, and tries to compare those properties to that of the Earth to see if we can find, we can truly find an Earth-like exoplanet out there. Obviously, the Earth has an Earth Similarity Index of 1. Mars has a similarity index under this kind of metric of 0.64, so pretty good, but not great. Jupiter has a value of 0.12, so very low. And then we have some favorable exoplanets on the left-hand side here. You can see some that you might recognize from press releases, for example. There is the TRAPPIST-1 system, which has 3 planets shown here, including TRAPPIST-1e, which is an Earth-sized planet with an Earth-type mass as well, but it's orbiting a much smaller star, so it gets a lot more irradiated. So that's why it's only at 0.85, so pretty good. And then next to that, we have a planet around our closest star, or one of our closest stars, Proxima Cen, right? So there is a planet, Proxima Cen-b, that has an Earth similarity index of about 0.85 as well. So it would appear that these 2 planets, and I guess others on the top row here, are very similar to Earth, such that artists are having a field day and trying to draw what these planets might look like, here showing what Proxima Cen-b might look like. I'm going to briefly mention atmospheres. Now, this could be a whole talk in and of itself, but basically, when an exoplanet goes and transits its host star, right? I told you before that it's blocking out a lot of the light from the host star itself. That's not technically true, because some of the light from the host star will go through the atmosphere of the planet, and any molecules or elements within the exoplanet's atmosphere itself will absorb some of that light. And so we can detect, if we put that light through a spectrograph, we can then detect if there are any molecules in an exoplanet's atmosphere. This is what's being done currently with Hubble and the James Webb Space Telescope. And so you can imagine that we might detect molecules such as water or sodium, or if we're on a planet that's very, very hot and doesn't really have much of an atmosphere, we might see titanium oxide from the ground itself being sublimated up into space. So there are some lava worlds out there that have temperatures of 1,000, 1,500, 2,000 Kelvin, in which the ground itself is literally being burnt alive, or being burnt, I guess, and emitted into space as titanium oxide. One of the interesting areas of exoplanet science, I think, that is coming up, and it's still a bit, this is where we have to actually, sorry, no, I'm going to mute this because I don't want to talk over the person. So one of the most exciting areas of exoplanet research to come up over the next decade, shall we say, is the detection of exomoons, right? I've told you a lot about finding exoplanets out there, but we still have not, spoiler alert, found an exomoon. No matter what this video that I'm about to show you kind of tells you. This was, however, a very exciting finding. So this is just an animation again of an exoplanet transiting its host star, right? The amount of light that we see from the system will decrease, again, depending on the size of the transiting planet. But now, if we just skip ahead a bit further, imagine, if you will, we have the same system, and we have an exoplanet that's transiting across the star again. So we see the amount of light will decrease when it crosses, when it crosses the host star. She'll stop speaking in a bit. There you go. And imagine, if you will, that there is a moon around this star. Now, it may also transit the star as well, in which you would get a secondary transit, as has been postulated in this data set. Now, these observations taken with, let me just go back here. These observations taken with Kepler are fantastic, but depending on how you analyze the data, other teams than the team that wrote this paper find that, in fact, there is a flat line after the initial transit, and so it's a bit tentative if this is an actual exomoon or not. But regardless, this is the way that we would find moons out there. And so I just wanted to kind of peel away the curtain for a bit and show you what might be interesting in the next decade of exoplanet science. With the last part of my talk, I want to briefly discuss the destruction of planets, or what happens to planetary systems when their host stars die. Now, I showed you this slide, I think it was my second slide, the life cycle of a star, in which, depending on the mass of the host star to start with, it's either going to evolve into a white dwarf or a neutron star / pulsar or black hole. as I alluded to, or as I kind of showed the artist's impression of, we have found planets around pulsars or neutron stars, but they are quite rare. Since 1992, we've only found, I think, 8 out of the thousands, so they are pretty rare in general. But what we have been more successful at finding is planets around white dwarfs, and this is an artist's impression of what we might actually be looking at. So I'll describe over the next few slides, but what we can think about this, if you want to kind of get a visual idea of what's going on here, this debris disk that we're currently looking at in this animation might be somewhat similar to just a scaled up versions of Saturn's rings. When a star goes through its planetary nebula phase, it ejects a lot of material such that the orbits of any planets that are going around it during the main sequence lifetime of the host star might be disrupted. So instead of having a stable orbit that, for example, goes around a star once every year, this orbit might be disrupted such that the planet then becomes more like a sun-grazing comet and comes very, very close to its host star, which, when that happens, the gravity of the host star itself will tidally disrupt the whole planet, rip it apart into shreds. Basically, you put a planet through a shredder, and you end up with this planetary debris that I'm showing here. At some point, this planetary debris will pass what's known as the dust sublimation radius, and the dust will go from being solid into a gas and basically fall onto the host star itself. The last case study that I want to show today will be highlighting the Spitzer and Hubble telescopes. You can see an artist's impression of the Spitzer Space Telescope up here on the top right. It was launched in 2003 and lasted all the way through to 2018, if I remember correctly. And of course, this is the Hubble Space Telescope taken with an image from the shuttle astronauts. It was launched all the way back in 1990 and is still kicking around today, 25 years after it was originally meant to be decommissioned. So how do we find these exoasteroids that have been disrupted? Well, if we look at this plot, which shows the wavelength of observations against their brightness, we would predict that the amount of light coming from a white dwarf by itself, so if there's nothing else there, if it's just a white dwarf star, we would predict it would follow this blue curve, right? We would have this amount of light that comes from a white dwarf star. However, for about 60 systems now, we are seeing that there is this excess amount of light coming from a system in the infrared. So this is why we'd use Spitzer, for example, which observes in the infrared part of the spectrum. And we have found that there is this excess of infrared light, which can be very well modeled by a disk around this white dwarf star. So what we imagine is going on is how I've described it, basically that the shredded material of a planet will then go into form this so-called debris disk, different to the previous debris disk, and again look something like Saturn's rings. We can also, as I've mentioned before, find the material that are in these rings as it gets fallen onto the atmosphere of the white dwarf, right? So if we have the material in the debris disk, at some point the gravity is going to take over and it's going to fall onto the atmosphere of the white dwarf. Now, white dwarfs should have hydrogen and helium atmospheres only. But in a few thousand white dwarfs, we have seen other features, or features, I should say, of other elements, such as the calcium-2 line that I'm showing you a spectra of here, which is basically these large absorption features here, is indicating that there's calcium in this white dwarf. Now, one of the interesting things about this observation is that it was taken 106 years ago. For the eagle-eyed amongst you, you may note this accreditation down here. That's because over on the left here, this is the original observation taken by Van Manen and his telescope operator in 1917, in which, ignore the bottom and the bottom and the top here, but if we look at this middle part, as this is a negative, we have to think of the flux decrease being bright here. These bright spots here, or this lack of black points here and here, is this calcium feature, which can only come about by a disrupted planet hitting this white dwarf star. So I told a bit of a lie again earlier in my talk in that we found the first planet in 1992, because that's not true. We found the first planetary material back in 1917, but at this time, no one knew white dwarfs even existed. So Van Manen and his telescope operator thought that this may be some weird kind of star, which indeed it was, but it also had planetary material in the atmosphere. This is a busy slide, and I'm going to go, I don't want to go into too much detail, but I want you to take away one key point from this slide. On the x-axis here, this is just a whole bunch of elements. On the y-axis, this is the abundance of the given element. And what I want you to have a look at here is the fact that the blue squares match up very, 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 very closely to the white and red stars. The blue squares are from a solar system asteroid, and the red and white stars are from a white dwarf. And so the material that is falling onto this white dwarf somewhere else in the galaxy is very, very similar to what we have in our backyard. Which, to me, I mean, I think that's incredible. Like, there's no reason that we'd expect the chemical composition of these things to be almost identical, but it seems like they are. In another system, we have found an exocomet. If you now compare the blue squares to the purple and red stars and triangles, we can see that the body that fell onto this white dwarf looks very, very similar to Comet Halley, which, again, we had to have no reason to expect that a comet in another system looks exactly like ours, but it seems like they do. I'm going to skip over these in the interest of time, but we can talk about them later. So hopefully, there's been a lot of material here. Hopefully, a lot of what I have showed you kind of resolves a few of the questions you had linking formation, evolution, and destruction. But what I want to kind of finish on here is just to highlight a few future telescopes, just very, very quickly to keep an eye out for over the next decade or so. This is a graphic from NASA that shows some upcoming space-based exoplanet missions. So we have, the Spitzer, Hubble and Spitzer, Kepler, TESS, which I've already mentioned, James Webb that was launched 2 Christmases ago. And then in the future, we'll have the WFIRST mission, which is also known as the Nancy Grace Roman Telescope now. It's something to look out for. Further afield than that, we'll have the New Worlds Telescope and HABEX and LUFOIR. On the European side, we have Corot and Gaia, which I haven't touched on yet, CHEOPS, which I mentioned before, and in a few years, we have the Plato space mission. We also have the Vera Rubin telescope that's currently being built down in Chile that will be when completed, it will be the largest ground-based telescope solely dedicated to discovering new solar system asteroids. And so this will be a fantastic use for building out our knowledge of the nearby solar system and for planetary defense. And then further afield, of course, we have the extremely large telescopes. On the left here, we have the EELT, or the European Extremely Large Telescope, that should come online in about 2030, give or take, and that's down in Chile. In the middle, we have the TMT, or the 30-meter telescope, that may be built on Hawaii. This is an American telescope. It may be built in Hawaii. It may be built in the Canary Islands. No one really knows. And on the right, we have the Giant Magellan Telescope, or GMT, which is another American telescope down in Chile. I'd like to, thank you for listening and take any questions. And whilst we do, I have one final video to show you the picture of our galaxy and where we discovered exoplanets across it. Now, I'm not sure if you can see that very well. I don't know if we can kind of enlarge on that. I don't think so. Well, you'll have to take my word for it that there are currently exoplanets that are being formed. We're back in 2002, or being found, sorry. You might be able to start to see some patterns, some red circles that are of exoplanets being discovered. We're now in 2007, 8, 9. You start to see it gets a bit busier. 2010, you might start to see a square of detections there in blue. This is the Kepler field. So remember the spikes in the graph that I showed really early on? This is Kepler doing its fantastic thing. And in the more recent years, we've had K2 and TESS that starts to really find more and more more and more exoplanets, until last year we hit the 5,000th exoplanet discovered. This video is on the NASA YouTube channel, so if you're interested and want to watch it in a bit more detail, there is also sound to this. You can go and, I would strongly advise you go and view on your own time. Thank you for listening.
Thank you very much. Thank you. That was excellent talk. Really, really interesting. Thank you. We'll take some questions. We'll start off in the hall here. If people on Zoom can put a message in the chat, and people on YouTube, if you can also put something in the comment if you want to ask. And I have a microphone if anyone wants to start the ball rolling. There you go.
Thank you for a very interesting chat. You mentioned that there's a handful of planets found around neutron stars. I just wonder if you can maybe have any thoughts why they managed to survive.
Yeah, this is a very good question. It's really hard to say. So as we kind of allude to here, there are like thousands of exoplanets found. We have only found 8 around pulsars. So it could be that the survivability is incredibly low to start with, of course. But then that begs the question, yes, your question, why are there these 8 that we know of so far? The likely answer to this is that they are initially formed very, very far away from the host star. So if we think further than Jupiter or Saturn in our solar system, and during the supernova, because of the distance there, then any material that will then hit these planets will have much lower density, basically, than if you were closer in. And so the orbits probably weren't as disrupted as any planets closer in. Since then, or since the supernova, the mass of the star will be much less because it's ejected a lot of material, right? Which means that by the conservation of energy, the orbits will move in somewhat. So you might have, and this is why they're probably detectable today, is that they formed further afield, stayed further afield, and then moved or migrated inwards to what we can observe today. That would be my postulation, should we say, but really we don't know the answer to your question currently. And yeah, I think the person to answer that will maybe not get a Nobel Prize, but get some kind of prize because it's very confusing.
Okay. We have one here.
Thanks very much for a absolutely fantastic talk. I have 52 questions, so I'm going to limit myself to one.
It's okay.
I was actually kind of interested in, firstly, I'm amazed that we're at a point now where at least we're talking about being able to detect exocomets and exoasteroids. That's really amazing. And I'm wondering about the level of data, the data set you're building up, because I think several years ago here, actually, we had another talk around planetary formation. And one of the big questions, as I understand it, looking at the history of our own planetary system, is how did a small wet world like Earth end up so close to its parent star when all of the water is far out? And what role did planetary movement, say Jupiter going in and out or Venus starting very far away and ending up, what role did that play in the late heavy bombardment and a huge amount of water coming into the inner solar system and happily landing on our little planet? Are we building a data model now where you could actually, given you've got 5,000 systems now you're mapping, where you can actually begin to answer some of the questions for us? Or are we still like 10, 20 years away from having enough? It's just conjecture still at the moment.
Yeah, this is another fantastic question. So I'll be interested in your 51 other ones. So we kind of have to come at it from two perspectives. So the white dwarf studies I finished on here, this is really giving us the compositional information, right? But these are, for lack of a better term, dead systems, right? We're looking at white dwarf stars. There's no resemblance of the solar system in these fields because we don't know where the planets came from in that system, right? We just know that, okay, we've accreted an exoasteroid or an exocomet, and they have compositions similar to Halley or asteroid in the solar system. That being said, because they look remarkably close, we can use these to infer that the fact that the 5,000 normal exoplanetary systems, which are still alive and kicking, should also resemble the solar system in compositional at least, right? So that's the first part. The second part, with the interior structure analysis that I showed, because we're getting the radii and the masses so precise now, and the bulk densities there, and then we use this compositional information, we can start to say if a planet would have water or not. And then, yeah, we can build up a library of these. Well, we're currently at the order of tens of well-characterized planets, but we are pushing more towards hundreds and thousands. So we can say that, okay, this planet has this orbital period and it has water. This one has this orbital period and it doesn't have water, for example. The next step beyond that is James Webb, and this is why it's going to be revolutionary for exoplanets. We can kind of do the same with Hubble, but it's not as great. But we can start to study their atmospheres, right? And so imagine, if you will, that we point James Webb at an exoplanet and we find water in the atmosphere of that planet. Then that is a conclusive evidence that there is water on that body, right? This is now, thanks to James Webb, relatively easy to do. And so we can, again, add that information to the library. So I think we're basically at the stage when we can do this. The next 10 to 20 years, we might get more precise observations, and we can maybe start to delineate between if planets formed outside of the waterline, or if they formed outside of the CO2 line or the CO line, or kind of more degrees of compositional information here. But we're really getting there right now. I hope that answers your question. It's a bit rambly, but yeah.
Anyone else in the hall?
Our own solar system, the planets' orbits are pretty circular. Have you any idea if that's common in these other 5,000? Are the orbits circular? Or would you never know yet?
Yes. So from one of the information, or pieces of information you get from the radial velocity method, is the eccentricity. So if if a planet is orbiting a star on a circular orbit, it will pull on its star in a very uniform fashion. But if it's on a very eccentric orbit, it will pull on the star very quickly when it's close by, and then when it's further away, very slowly. So we can detect this, we can get this information. For the vast majority of planetary systems that have Earth-similar planets and a collection of Earth-similar planets, they are all on circular orbits. However, we have found Jupiter-only systems in which the single Jupiter in that system is on a highly eccentric orbit. Now, this has a few interesting implications in that something must have happened in that Jupiter's past to make it on this highly eccentric orbit. Probably gravitational interaction with another Jupiter in the system that then got flung out of the planetary system. But that also means that anything, or the atmosphere of that planet will become very, very hot as it comes closer in, and then very, very cold as it goes further away. So exactly, depending on the variation, depending on the temperature of the host star, there's going to be a lot of changes going on in this planet. And would there be moons around this thing, right? I mean, we don't know the answer to that question yet, but there are these very highly eccentric Jupiters out there. But if there were any Earth-like planets in those systems, we have no idea, because the Jupiter would have just destroyed everything. So we don't know.
Any other questions in the hall? Oh, sorry.
When using the transit method to detect the exomoon, how do we tell the difference between an exomoon and just another planet? Sorry, I didn't mean just another planet.
No, I'm not laughing at that. I'm laughing because this sounds like the referee feedback I got on one of my previous papers. No, this is a very good question. The short answer is we currently can't, right? You're absolutely right in that if you have the planet and it's making if you have a planet and it's making a very deep transit, you might just have a planet further from its host star, or just a smaller body like a Mercury-type body, for example, nearer to the host star, and so you'd also get this dip. We can't whether it's a moon or a small planet, we wouldn't be able to tell from one observation. But if we take repeat observations, unless the planets are very close together in their orbits, we would expect the transits to either start to space away from each other. So, if the hot Jupiter has a 2-day orbit, so you'd measure a transit every 2 days, and the other one has a 3-day orbit, for example, then you'd see the other transit at a different time if you were to keep staring at it. If it's a moon, it should come back and you'd observe it in roughly the same place. But if you just have one observation, as was this study, you can't really tell it apart.
Yep. Okay, I think we'll probably go to Zoom questions if there are any. No Zoom questions, any YouTube questions?
Just same questions.
All right, okay, right, so that's fine. Yeah. I have one more question here. Oh,
do you find that rocky planets are more nearer to stars than gaseous planets in general, or can it depend on the system?
Yeah, it kind of depends on the system. So the interesting delineation that we found is that with over 30 years of observations now, what we find is that there are in general 2 types of planetary systems. There are hot Jupiter systems in which you have a single Jupiter in a very tight orbit around its host star that probably has cleared out a lot of the other planets that I was talking about before, and that's the only body there, right? It's that one guy and that's it. And then the second type of planetary system is there are these very compact small planetary systems. So we might have a chain of 2 to 3 to 4 to 5 Earth-sized planets that are very close in to their host star. Now, I'll caveat their answer with the fact that we are observationally biased and it's easier to find planets that are closer into their host stars. So we don't really know what's going on, like beyond the snow lines, for example. But at the moment, we seem to find everything everywhere, but within these 2 kind of architecture configurations. Yeah.
that's great. Thank you very much again, Kerry. Thank to Tom again for that. Thank you. Okay, we'll just have a quick changeover, and Sean is now going to tell us about the sky in March. Okay. Thank you.
Okay, can everyone see that? Yes? Can you see it? Yeah? Good. Excellent. Great. Sorry, schoolmaster mode. Ask a question, get an answer. Yeah? Yeah, well, I can't, but if someone else could, it would be... there we go. Is that slightly better? Okay. Right, just bear with me 1 second. Okay, so hello, good evening, everyone, and thanks again for such a fascinating talk so far. So this is my first time actually presenting a presentation on the sky in any month, let alone the month of March. So let me just make sure this is moving on correctly. Yeah, okay. So very briefly, just a kind of an overview about what I'm going to talk about this evening. Obviously, talk about the sky in March. A quick word about the planets, although I'm feeling rather intimidated given the presentation we've just had. So we've gone from PhD to the Blue Peter version of a discussion on the planets, what you're going to see, or at least the naked eye planets, I should say, for this month. Some stuff about the deep sky, some of the nice images some of our members have taken recently. I'm going to then vent my spleen on something, and then we'll talk about what happens in the month of March. So, Before I go any further, as plagiarism is the highest form of flattery, I have to and want to recommend the fact that I have just viciously ripped off the excellent monthly article by our dear friend and colleague Alan Pickup, which is published in the Scotsman every month. You'll find that screen grab there is actually from the featured news section of our website. If you have time, I suggest you go onto our website and use that link to go and look at Alan's full article. It is always a treat to read every month. It's just enough to keep you interested, but short enough that you can digest it quickly, so you know what's actually happening in the month. So I wanted to give Alan full credit for his amazing work, which I'm now just going to pretend is my own. So I think almost every speaker uses Alan's graphs to start off their presentation, so I'm not going to break with tradition. So these are the graphs that Alan has produced for the month of March. And as you'll see over there on the left-hand side of the screen, yes, that's correct, we have the times, so that this graph is correct for 2300 GMT on the 1st, which was on Wednesday of this week, about 2200 by the time we get to the middle of the month on the 16th, and about 2100 GMT, which of course is 10 p.m. British summer time by the end of the month, because by then the clocks have gone forward. And again, I don't know if you can see, can people see that cursor? You can, yes, okay. So looking north, we're at a stage now in the year where the plough is pretty much, the Ursa Major is pretty much at the zenith overhead. We've got the winter constellations are now starting to set in the west. Venus is rising in the east rather spectacularly. I'll talk about that in a moment. In the west rather. We're just starting to see the beginning of the summer triangle come up as we head out into the spring. Looking south, well, most of the winter we've had the treat of Orion, as we normally do, out to the south, plus some very good naked eye planets in both Mars and Jupiter, and I'll speak about those again in a second. The southern sky, it depends, of course, where you are. This chart is prepared for Edinburgh and our latitude. Of course, I'm aware that thanks to our online presence now, we have people watching perhaps at far lower latitudes and maybe even some watching at higher latitudes, who knows. So again, there'll be corrections around that depending on where you're based. So looking at the nighttime sky, and these are just screen grabs from the Stellaria map. I'm sure you'll recognize them. This was looking west at the time the meeting started this evening. If you walked here this evening or drove here this evening, you could not fail to miss the spectacular sight of Venus and Jupiter together in the western sky. They're currently having a conjunction, and sadly, they were at their closest point on the 1st of the month, I think. And I say sadly because we were blanketed in cloud in Edinburgh, so we didn't get to see it, nor did we get to see it last night. Tonight, however, is gloriously clear, although the planets are not as close as this graph would suggest because of the zoom that this was taken at. And I'll speak a little bit more about that shortly. Sorry, I just want to keep an eye on my time here as well. But yeah, so we've had setting in the west now in the evening. Obviously, Taurus and the Pleiades and the winter constellations are now starting to go down in the evening. Looking at Orion is now dipping down into the southwest in the western sky in the evening, and as I mentioned earlier, some of the constellations we associate with the spring and the summer are now starting to rise. If we jump forward to the end of the month, looking west, you can see that the sky has rather changed dramatically. Firstly, you'll notice that Jupiter has vanished, and I'll talk a little bit about that in a second. Venus, however, is dominating, and this is a wonderful time to look at Venus. I know from my own work that apart from obviously the joy of looking at the sky and it being such a fascinating thing, this is also a busy time for the emergency services. You would be amazed how many people dial 999 when they see Venus in the sky, mistaking it for all sorts of things, crashing aircraft, distress flares, people signalling from another world, etc., etc. Errant helicopters, we get a lot of that. So yeah, if you're currently on duty tonight at the Police Scotland call centre at Bilston in the east of Edinburgh. You start getting 999 calls over a bright object in the sky. They'll know what it is. You'll also notice by the end of the month we're starting to see Mercury. Mercury is, I've been amazed over the years coming to these meetings and talking to people and talking to professional astronomers, which is always a joy, only to find out they've never actually seen Mercury with their own eyes because it's such a difficult planet to see. And when you live in cities like most of us do now, it's even harder. So it's currently not visible at the moment, but as we head into April, it will start to become visible. You'll also notice Mars is now starting to dip down in the evening sky as well. Mars and Jupiter have given us quite a lovely display over the winter in the southern sky. We've been quite lucky for them as optical planets. They've been on display, and again, I'll speak a little bit more about those in a while. So looking north this evening, again, this screen grab didn't go. I've got too much west and not enough east in this, but you'll see that in the evening time, the asterism of the Plough, or Ursa Major, is starting to come up and rise up towards the zenith. Personally, I've always thought it's an extraordinary thing when you go out in the evening and look for the Plough, and you have to look directly up. It's probably the only time of the year you do that, and there's something, to me personally, quite exciting about that. Rather than just looking into the northern sky, you're effectively having to look directly up. You'll notice that some of the other shapes that we recognise in the sky, like Cassiopeia or the arc of the handle from the Plough pointing down towards Arcturus, which will be rising as the month goes on, are now starting to appear. If we look into the north again for this time next month, you'll see that the Plough is now much further higher up in the sky earlier in the evening, and again we're starting to see the beginnings of the summer triangle coming into the evening sky. Looking east this evening, again, you'll have noticed if you look the other direction when you were coming in this evening, we have a moon up, and we also have constellations like Leo and Cancer rising in the east at the moment, and again, those are very typical of the spring. It's kind of a cursor that the spring is coming when you see these things arrive, so that's always a lovely thing I think to see. By the time we get to the end of the month, looking east, again, all of this is from Edinburgh, of course, and it's for 7:30 p.m. by now British summertime. You can see that the constellation of Bootes the Hunter is now appearing in the evening with that lovely red star Arcturus, and indeed you also have Virgo with its bright star Spica, which when I was young I was always told was the hottest star in the galaxy. I guess it was back then. I'm sure it isn't anymore. I'm sure there are stars with a surface temperature that are much higher than Spica now. But again, this asterism that you follow the handle of the Plough around, and it leads you to both Arcturus in Bootes and Spica in Virgo. There are many other asterisms. I'm not going to bore people with them at the moment. Looking south, this is looking south this evening, and again, looking south is always fantastic. You've got Orion, which is beautiful any time of the year, even if you never look at a telescope or even look through binoculars. Orion is always such a fantastic object just to look at with your eyes. But we're doubly lucky at the moment because we've had both Mars and Jupiter high in the southern sky. They're still in the southern sky in the evening, although they've dimmed a lot now since the winter period. But we have wonderful objects to look at, like the Pleiades in Taurus, which I only found out from coming to these meetings. In Japanese culture, they call it Subaru, which is what the model of car is called after. And I think it was Alan that might have told us that once. In fact, if you look at the badge on the front of the Subaru car, it's actually the Pleiades. It's that's the corporate logo they have on the front of the car. So I've never owned a Subaru, but if I ever have the money, who knows, I might get one just because it has the Pleiades on the front of it. As I said, the moon is up. We're heading towards the full moon. Full moon will be in, I think, about 3 or 4 days from now. We still have Sirius, the brightest star in the sky, though it's paling in comparison to Venus at the moment. You really had a line of very lovely bright objects out to the south for the winter, such as Betelgeuse, Mars, Capella, etc. By the time we get to the end of the month, however, things have changed. You'll see Venus is still quite high in the sky, and Mars is still there, but Orion is really now starting to fade down into the southwest, into the evening twilight. and we're looking towards more of the summer constellations starting to creep up and come into the night sky. So that was me rattling through my attempt at trying to describe the night sky. So what are the planets doing at the moment? Apart from forming, living, becoming extinct, unable to afford their mortgage, etc. So Mercury, Mercury, as I said, is one of the hardest planets to see. I've only ever seen it once personally, and that was from Spain many years, I think 2013. And I hadn't realised I'd seen it. It was only on the second evening I realised what I was looking at was Mercury. But for most of this month, it's not visible because it's been behind the sun. However, as we get to the end of the month, it will start to appear in the western sky, quite low. April will be a better month to see Mercury than March. But nonetheless, as we head towards the end of the month, you should try and look to see if you can find Mercury in the evening sky. Basically, look towards where the sun has set. After the sun has set, needless to say, preferably on a flat horizon, where you've got a good view of the horizon, and you may see Mercury. I think it gets up to about magnitude minus 1.3 by the end of this month, so it should be visible in the evening twilight. No need to tell you what the superstar of the month of March is, and that's the planet Venus. It is dazzling. It's dazzling now. It will get even more dazzling as we go through the month. You can see there currently it's at magnitude minus 3.86, which makes it the brightest object in the night sky after the full moon. It's so bright you can see it in streetlights. I was at the bottom of the Royal Mile about an hour and a half ago, and I could, despite the fact that they were visible streetlights shining right in my face, you could easily see a Venus. So it's always wonderful, and it's a great way to, I think, engage people, despite those who get panicked when they see it and call for help. It's about 1.37 astronomical units from us at the moment, and you'll see that as the month goes on, it climbs in the western sky. It gets up to about magnitude minus 4, so it's going to be really dazzling. Unfortunately, its dazzling partner Venus will have vanished by then, but nonetheless, we can all enjoy it throughout the month of March. Mars has been giving us a good old performance over the winter. It's been really nice to see, actually, Mars. One of the nicest things I found about looking at Mars the last couple of months is how bright it's been and how high up it's been in the southern sky. And it's always interesting because there's lots of other red objects in its area, like Aldebaran or Arcturus. And therefore it's been kind of easy to pick out because it's the odd-looking red spot of light where there isn't usually a red spot of light in the night sky. So, but as you can see, unfortunately, it's now starting to wane as we pull away from it. Given that we're in track number 3 of the Olympic running of the planetary running ring, and it's in track number 4. We're now rounding the bend, so it's currently at magnitude 0.44, but that'll decrease to magnitude 0.95 by the end of the month. So it's going to get very much dimmer and really get lost in the evening haze as we head through the month. Jupiter, the king of the planets, and for those of you who are currently short of fruit in Little Aldi, I just thought I'd remind you of what a nice piece of fruit looks like. Currently, it's don't get me started. Currently, it's in the western sky. You'll have seen it this evening. It's been putting on a dazzling display in the south over the last couple of months, but it's now again we're starting to pull away from it, and it's about to, from our point of view, head around the back of the sun. So while it's still at just under magnitude -2 at the moment, and it's in the evening sky, by the end of the month, it will have vanished below the horizon before sunset. So we will lose it for a while, but it will become a morning object later on in the year. But it's just it's a great planet to look at. And in fact, if you look at it right now, even with my little camera phone that I took a photograph with earlier, if you zoom it up, you could clearly make out the Galilean moons from a street in Edinburgh, which I think is fantastic. Not as good as discovering exomoons, but still not bad for an iPhone 12. Saturn is not putting in an appearance at all at the moment. It's on the huff, which is a nice way of saying we're just the wrong side of the sun at the moment. And I think if I'm right, we're also heading to that point in Saturn's orbit where its rings are almost edge on to us, or they very soon will be in the next 2 or 3 years. That odd time in its orbit when, if you look at it through a telescope, it looks as if it doesn't have a ring system anymore because you're literally looking at it edge on. For the next 2 years, we're going to see how that pans out. It was bright in the southern sky over the winter, but again, depending on where you are, it's now well lost effectively in the evening. So, I mean, the main show of this month is really the conjunction between Jupiter and Venus, and it's a pity that we missed it here in Edinburgh. But as I mentioned earlier, Venus is currently at magnitude -4, so it is dazzling, and it's also wonderfully getting higher in the horizon at the moment. Around dusk, it's about 24 degrees above the horizon, but by the end of the month, it'll be up around 30 degrees, so it'll be unmissable in the western sky. And it's a great way to get people who wouldn't normally look up at the night sky or normally pay attention to what's in the night sky. It always attracts their attention. It's usually better when it's an evening object because more people will see it than when it's a morning object, unless you're weirdly on your way to work, and by then you're probably looking more for Starbucks than you are for planets. But one of the facts that I picked up from Alan's article, which I thought was very interesting, was that while we see a conjunction of these two planets almost every year, the current conjunction is the best in terms of brightness and distance above the horizon until November 2039 from Scotland. So enjoy this period because between now and the end of the 2030s, the other conjunctions won't be as spectacular from our current location. Of course, it's not just planets. We've got lots of deep sky objects in to look at as well, and you can. You don't need to spend thousands and thousands of pounds on expensive equipment. If you have a good pair of binoculars and go out and you know where to point them, you can really see so much. I haven't put too much in about this. I've just picked one or two of what I thought maybe wasn't too much the usual suspects. One deep sky object that's in the eastern sky right now, though it's close to the moon, so it's probably hard to see tonight, is M44, better known as the Beehive Cluster in Cancer. This star cluster, this open cluster. This image is actually from our own website, but it's a really lovely object to look at. If you go out and look at where the moon is tonight, that will give you some idea of where to look for it when the moon has moved. Cancer isn't one of those constellations that sticks out very well, particularly not if you're under streetlights. It's not like a Leo or an Orion, which you can always pick out easily from the shape. Usually, the easiest way to find Cancer is to look between Gemini and Leo. If you know where the twin stars of Castor and Pollux are in Gemini and where the backwards question mark is in Leo, then Cancer is about halfway in between those two. So that might be an object you want to try and take a look at over the month if you have a good pair of binoculars and the sky is clear. Another object which you would definitely need a telescope for, but which is very close to, at least I say close, in the same part of the sky, I should say, from our vantage point on Earth, is NGC 2638, betterwise known as the UFO galaxy. Again, it's effectively between Cancer and the constellation of Lynx. That's not a deodorant, that's a cat, but still. It's in the kind of area that if you do have a telescope and you're practiced at these things and you know where to find the Beehive cluster, then it shouldn't be too more difficult to navigate your way to that galaxy. This image is actually just taken off the internet. I think this is from NASA, but it's a beautiful object to look at if you have the time to search it out. We have no shortage of unbelievably talented astrophotographers in our society, and it's a great joy. My standard is rubbish, but we have other people who try a lot harder than I do. And one of them is our friend and colleague, Pat Devine. She took this photograph on the 20th of January, and of course it's the Andromeda Galaxy, M31. The Andromeda Galaxy is great for lots of reasons. Firstly, it's our galactic twin. It's very close by to us. At some point in the very distant future, it and the Milky Way are really going to integrate with each other, quite literally. None of us will be around to see that. But it's usually easy to find. It's often high up in the northern sky. And of course, in terms of if you're in a dark environment like out in the countryside, it's the most distant naked eye object. If you practice looking at it out of the peripheral vision of your eye as the fuzzy blob that's sort of 2 stars above the constellation of Cassiopeia, find the right-hand corner of the great square of Pegasus and follow the curve of stars up from that. Over Christmas, I had the great joy of being with my 11-year-old nephew in Ireland, and he saw it for the first time through the pair of binoculars he got for Christmas and was overjoyed. And now you can't drag him away from looking at the night sky, which I'm secretly delighted about. I don't think his parents are that happy, but tough. You'll be aware in the last couple of weeks, or days, I should say, you'll have seen media reports about the fantastic aurora we had the last couple of nights. And the aurora is one of those events that it's really easy for the media to pick up on and therefore really easy to engage public interest in. I'll come on to the issue of the media in a second, but this image was taken of the Northern Lights, or the Aurora Borealis, by our friend and colleague Andrew Farrow, who I don't think is Andrew here tonight? No, he's not. Okay. But this was taken on the 27th of February, and you can see just how you can actually just make out the W of Cassiopeia there in that section. Maybe it's hard to see on the screen. I apologize if it is. The lights might be deflecting, but Cassiopeia is just there, so you're looking effectively north there. Fran Goodman took, these are 2 separate images from Fran taken on the same night, 2 beautiful images. One she's, these are her titles, I should say, not mine. One she's called The Hunter and the Kirk. The Hunter, of course, being the constellation of Orion, which is here. That's Betelgeuse, that's Rigel, that's the Belt and the Sword of Orion. I don't know where this Kirk is per se. I'm guessing it's somewhere in Edinburgh or near Edinburgh. But sorry? Aberlady, I've just been told by Mark, it's in Aberlady, and I just thought it was a lovely composition and really, really nice. She also got this lovely shot of the conjunction of Jupiter and Saturn, Venus and Jupiter, I should say. This is looking west. I think those are the lights of Edinburgh out to the west. And again, it just shows how I suppose how lucky we are to have an interest in an area of nature where it's very easy for people to just look up and see these things, and if that gets them more interested in finding out more is the better. David Harvey took this photograph. I'd be very impressed if he took it personally. He's obviously using remote telescopes here. He took this mosaic on the 25th of February of the M84 galaxy chain in Virgo. And I just thought it was a lovely composite image. It almost looks reminiscent of the Hubble Deep Field. When you first glance at it, I thought that was actually quite amazing, and it was something that occurred to me when I was listening to the talk earlier today about how maybe it's just the human eye and the human brain, but how you see patterns repeating in nature. And how that's a really beautiful image to have. I should say all these images are on the Astronomical Society of Edinburgh's Flickr webpage, so please feel free to go on there and look at them yourself. There's many more. I just picked a few. Our president, Mark Phillips, produced this mosaic. Sorry? Oh, isn't it? Could you know who it is? Ian's, all right, okay. Well, my deepest apologies then. It's Ian Smith. And Ian, if you're listening online, I have no doubt I will be rebuked, rightly so, I should say, and my apologies for that. Well, Ian Smith, our good friend and colleague Ian Smith, produced this extraordinary image, mosaic image of the Soul Nebula and the Heart and Fishhead Nebula in Cassiopeia. And again, it's just one of these images. I think there's actually, you can tell from the dark area down here that these are 3 images spliced together. But I'm in awe that anyone can do that I know. Quite frankly, I can barely take a selfie of myself. Usually I get the top of my head or my chin. But I just thought that was a beautiful image that's currently up. So Ian, my apologies for mislabeling you on that one. Peter Black, our vice president, took this image of the moon just a few days ago on the 24th of February. It's a beautiful image. It's the waxing crescent moon, which I think, again, is always one of those things that people find so interesting to look at. Obviously, most of the surface features of the moon are in relief because the sunlight is cutting across them at an angle. And it's an image that is both, visually and culturally resonant for so many cultures across the planet. And again, it's a great way of engaging the public. And that kind of leads me on to actually just a little bit of a discussion, or not a discussion, but an observation, I should say, about how we engage the media. We here in the Society spend a long time talking about how to interest the public in astronomy or the sciences of astronomy, and I guess how to keep them engaged, how to explain complex things in an engaging and entertaining way, and certainly our guest speaker did that tonight in bucket loads. So that's a great thing to do. The reason I'm saying this is because of what I'm calling the supermoon thing, which has become more and more prevalent in the media in the last couple of years, and I've oscillated from being, pardon the pun, super annoyed to going, well, actually, I suppose it's not that bad, to going back to being super annoyed again. But I just thought I'd have a quick look at it tonight, given that the moon is up, and just where did this all come from, this whole media fascination with the supermoon and what it does. Well, part of the reason I'm annoyed is that I several of my work colleagues know that I have a great interest in astronomy, and I don't know whether they do this just to get a rise out of me or whether they genuinely confuse it, but the amount of times I've been introduced as an amateur astrologer, I know, thank you for groaning. People come up to me and say, I'm a Sagittarius, what do you? And go, I'm annoyed. But nonetheless, apparently the US astrologer Richard Knoll in 1979 coined the term supermoon, and he defines, and I use the term define in the loosest sense of the word, a supermoon as a new or full moon which occurs when the moon is at or near within 90% of its closest approach to Earth in a given orbit, which is actually not a bad definition in one respect, if you're going to label something. But it occurred to me, on the one hand, a supermoon is a great thing to engage people with. It gets lots of news coverage. It's a good filler story for 24-hour rolling news media. If you've got to talk about something at 4 a.m. when nothing has happened in the world, and there happens to be a supermoon happening, well then, good. Usually, today the standard seems to be getting photographs of people in Hong Kong looking at the supermoon across Hong Kong Bay or some other dramatic panorama. But of course, we humans are obsessed with shiny things. We spend a lot of our time looking at shiny things. If astronomy is right, then something like only 4% of all the matter in the universe is shiny stuff that either emits light or reflects light. So 96% of the stuff out there is not shiny. So it's natural in a way that people, and through people, the media would be interested in shiny things. But the reason I was inspired to actually put this slide in tonight is that we actually had perigee, or the moon was at its closest in its orbit twice last year in November and December. But you didn't hear anything about a supermoon because it happened when the moon was new. So it was on the daytime side of the Earth. We were looking at its nighttime side. We couldn't see it. Therefore, there were no worried stories on... that's my timer to shut up. There were no worried people phoning, worried about tidal waves, tsunamis, plagues of locusts, the planet being pulled off its axis, and various other things that might happen with a supermoon. Why should the supermoon be so dangerous when it's a full moon and not when it's a new moon? The answer is it's not. It's just we pay no heed when we can't see it. The other thought that led me to is that obviously when the moon is at its farthest point from its orbit apogee, you never hear anyone talking about a mini-moon, the dangers of a mini-moon, and what could the effects of a mini-moon be on human society or on our psyche or our mental health or the domestic habits of farm animals, etc. but I just thought it was an interesting thing, and I've oscillated tonight between whether it's a good thing or a bad thing. I suppose in a way, it's a good thing from a purely PR point of view if it engages people in the topic of astronomy, or in the sciences of astronomy, as I should now say, because astronomy hasn't really been a singular science for about 180 years now. But you know, it's a foot in the door to get people interested, and even if it's just to explain this to them and say, why do you not worry when it's a new moon? And get them thinking about that. So maybe a supermoon isn't the worst label to have, much like the Northern Lights isn't the worst label to have. I know it annoys some people here in society when you see these things being butchered in the media, but look, it's to quote a former countryman of mine, the only thing worse than being talked about is not being talked about. So I guess on that basis, it's maybe a good thing. I'll let you make your own mind up. And just finally, a quick reminder, obviously March is that time of the year when, one natural event and one completely contrived event happens. The contrived event being we all put our clocks forward. This year it'll be the last Sunday of March, which is the 26th of March. We will go from GMT to British Summertime, BST. So our clocks will go forward 1 hour. That will obviously affect stargazing in the sense of, obviously, the evenings are now getting much brighter, so it will become harder to look at objects as light proliferates in the sky. The other more important thing, of course, is that we're approaching the equinox. This year it happens to fall on the 20th of March. That's the moment of the equinox, 21:24 GMT to be precise if you're here in Scotland. In other words, when the sun is directly above the equator. And the little graph on the right just shows you what's effectively been happening to the planet in that period between September and March, or rather that period between sort of November and February, really, where we're at the December solstice. The majority of solar radiation is falling on the southern hemisphere because the northern pole is pointed away from the sun. In the summer, for us in June, it's the reverse. But at the equinoxes in March and September, because we're at right angles, that effect is nullified. And so if you happen to be anywhere on the equator at midday on the 20th of March, if you're lucky enough to be on the equator that day, then, I was about to say, look up, but don't look up. Don't look at the sun. Look down, and you shouldn't have a shadow. There's, if anyone, I know some colleagues will know Hawaii very well because they'll have worked there, but if you ever happen to be lucky enough to be in Honolulu, there's a public park in Honolulu where there's a public sculpture which kind of looks like a very large piece of pasta that fell off the back of a truck. But it's designed in such a way as that when they have what the Hawaiian Society call the high noon, which is when basically when the subsolar point is on the island of Oahu directly under it, the shadow of this object forms a perfect circle on the ground. And it's the only time of the year that happens. I just thought I'd remind us all that the equinox is actually quite a good time to get interested in these things. And that's it from me for March. Thanks very much.